this lecture, we are going to talk about power spectrum analysis of switch mode power converter using mixed signal oscilloscope. I am Dr. Shantanu Kapat and with me Nitin Nigam from Keysight Technologies. In this lecture, we are going to consider time frequency domain correlation of signals in switch mode power converter and instability in switch mode power converter and their corresponding power spectral density. And here we are going to consider a buck converter, digitally controlled buck converter prototype, and Nitin is going to demonstrate using mixed signal oscilloscope how to capture power spectral density and how to characterize the power spectrum.
Hi, in this lecture we learned about how to do the frequency domain characteristics and the time domain correlation between both the signals together. It is very important to do this correlation in the oscilloscope. It helps us to understand a much deeper analysis of that particular signal. For doing this experiment, we have taken inductor current signal on the oscilloscope connected on channel number 2. When we do a specific measurement related to the particular signal, if we are doing the frequency specific measurement, we could see the frequency specific of that particular measurement is 200 kilohertz. Add measurement. So as you can see, the frequency that comes out is 200 kilohertz. When we are doing the spectral measurement of this, we need to switch on the FFT function which is available in the menu, and we can go to the specific channel and switch on the specific function related to the frequency. We could see on the bottom side the time domain signal and the frequency domain signal coming together, and we could easily identify the first frequency which is at 200 kilohertz, and furthermore we could see the harmonics of that. It's very easier to correlate the time domain signal and the frequency domain signal together, and if there is any changes specific to the signal load, we could see what are the other frequency component that has been introduced into the specific measurement. Thank you.
Okay, I think Nitin has already demonstrated about how to get the power spectral density of the switching signal. So here I want to add some more information. Here you can see this is the inductor current of this buck converter, and we are running using inner closed loop. I mean, that means it is a current mode control where only inner loop is closed, and it is a mixed signal current mode control. We have not closed the outer loop. So in this condition, the converter is running under stable periodic behavior. It shows the periodically stable behavior, and corresponding spectrum you can see if you take the power spectral density of the inductor current FFT, then you will see because it has some average value. So average coming, that means that low frequency will get the DC component, and then this is the 200 kilohertz, and then this will be 400 kilohertz, 600 kilohertz harmonic. So 200 kilohertz is the switching frequency. That means this is my fundamental component. Now this is under stable periodic behavior, and under pulse width modulation, fixed frequency pulse width modulation, this is the power spectral density. Now what will happen if you find instability in the converter, that means the cycle by cycle instability. So under this condition, we will discuss about the inner current loop stability. If we reduce the input voltage, that means we already know that in our earlier NPTEL course, also in earlier lectures, that current loop will become unstable if either you keep the current difference same and decrease the input voltage, then the duty race will increase. And let us see, we are decreasing the input voltage, and as a result you can see now duty ratio is changing. Now as we further decrease the input voltage, you can see there is a subharmonic instability. So now this subharmonic instability is coming slowly. This is like an unstable behavior. So you can clearly see subharmonic instability. That means as if it is repeating after 2 switching cycle. As a result, you have one frequency content coming at 100 kilohertz, whereas the switching frequency is 200 kilohertz. That means using power spectral density, we can characterize what is happening for switching converter when the cycle by cycle stability is lost, and this is subharmonic because our fundamental frequency is 200 kilohertz, whereas the another spectral peak is coming at 100 kilohertz, which is half of the switching frequency. Similarly, if you further decrease the input voltage, you will find more unstable behavior, and it may lead to even high periodic as well as chaotic behavior. So that means the major main takeaway of this particular lecture is that you can clearly evaluate the power spectral density of a stable as well as unstable behavior of a switch mode power converter. Thank you very much.